Welcome to another simple engineering snippet. In this snippet, we will be calculating the optimal turbine blade speed. We will be using conservation of mass and conservation of momentum for a moving inertial control volume. Our task is to find the optimal turbine blade speed that maximizes the power extracted from a fluid stream. Let's isolate the actual blade for our analysis. Now let's set up to solve the problem. We need to define a control volume. For this analysis, we will define the fluid in contact with the turbine blade as the control volume. We identify that there are two surfaces with flow crossing the boundaries. The inlet is labeled as surface 1, the outlet as surface 2. The outward unit normals are shown for these two surfaces. We also need to define a coordinate system. It is shown here. We will be utilizing the following assumptions. These are fairly standard assumptions for this type of analysis. Deviations from these idyllic assumptions are typically accounted for when we calculate the turbine efficiency. These are the equations that we will need. The turbine blade is moving at a constant speed, so we will be utilizing a moving inertial control volume approach. The relative speed is defined as the difference between the fluid velocity and the control volume. The equations for conservation of mass and conservation of momentum are the same as used in a previous instructional snippet for fixed control volumes, except that we have substituted in the relative velocity for the fluid velocity. We can also note that since we will only be using the conservation momentum in the x direction, we have dropped the vector notation. Let's look at surface 1 to determine the relative velocity. The relative velocity is the fluid velocity you would see if you were moving at the same speed as the control volume. In this case, if the blade was moving at the same speed as the incoming fluid, you would see a fluid velocity of 0. If the blade was fixed, then you would see the full velocity of the jet as the fluid velocity. The relative velocity at surface 1 is the jet velocity minus the blade velocity as shown. Now let's look at surface 2. This time the fluid exit velocity is in the opposite direction to the blade. The relative velocity is the exit velocity of the fluid plus the blade velocity. Now let's use conservation of mass to relate the relative velocity at 1 to the relative velocity at 2. Since the flow areas and densities at surfaces 1 and 2 are the same, we have that the relative velocities are also the same. We can now solve for the fluid velocity at surface 2, which is equal to the jet velocity minus twice the blade velocity. Now let's apply conservation of momentum. The first thing we must do is pick a direction for the reaction force the blade places on the fluid control volume. This is shown in red and labeled as Rx. I have assumed or guessed that it will be acting in the negative x direction. If the solution results in a negative value, then that means it is acting in the opposite or positive x direction. I have another snippet that goes into painful detail on how to apply conservation of momentum, so I will skip the details here. At this point, however, I have kept the terms separate with an explanation on the signs, since this is a very common source of error. Now we do some algebra to solve for the reaction force. At this point, we have enough to confirm that the reaction force is indeed acting in the negative x direction. We solved for the reaction force, but we really want power. Power is equal to force times velocity. How much power the turbine blade is extracting from the fluid will be equal to the blade velocity times this reaction force. Now that we have an equation for blade power, we are left with a problem from Calc 1. We take the derivative with respect to blade speed and set it equal to 0 and solve for the roots. The details are provided here. We end up with a quadratic equation and thus two solutions. The first solution, the blade speed is equal to the jet speed. This is for the minimum blade power. If the blade is moving at the same speed as the fluid, then it will not be extracting any energy from that fluid. The second root gives the maximum power. The optimal blade speed to extract power is equal to the fluid jet speed divided by 3. Many will know that the ideal blade speed for this type of turbine is actually equal to the speed of the jet divided by 2. Where did we go wrong? Our mode It's too late for me, but okay, never mind that. It turns out that both are correct. The explanation lies in that we analyze for a single blade. The delivered power is the specific work, or work per unit mass, times the mass flow rate that hits the blade. With only one blade, then the amount of mass that hits the blade is a big player. In reality, turbines do not have just one blade. In academic problems, you will often see the phrase, "the turbine has many blades." The mass flow rate that misses one blade will hit another. Is this perfect? No, but the difference between this model and reality will be counted for as a turbine loss and factored into the turbine efficiency. All is not lost. We can just repeat our calculations and manipulate the equations so that all the mass impacts the blade. As fun as that may be, there is a simpler way. The turbine is converting kinetic energy of the incoming fluid into work. Conservation of energy tells us that the kinetic energy of the fluid jet is equal to the kinetic energy exiting the turbine plus the turbine work. The maximum amount of work is obtained when the kinetic energy exiting the turbine is zero. Luckily, we have already solved for the fluid velocity at the exit in terms of the jet velocity and the ideal blade speed. We can set this velocity to zero and solve for the ideal blade speed, which is equal to 1/2 times the jet velocity, which is as expected. In review, for this type of turbine, the ideal blade speed is equal to 1/2 times the jet velocity. The analysis for a single blade is 1/3 the jet velocity. Did I waste your time? Well, possibly, but my real intent was to work a moving inertial control volume example. There are, though, many applications for the approach we used for the single blade, so I hope it was a good review. The ideal blade speed equal to 1/2 the jet velocity is true for a single stage turbine. How to determine it for a multi-stage turbine will be the topic for another instructional snippet. I hope you found this instructional snippet helpful and not too annoying. Please like and subscribe and have a great day.